here. So today, we're going to discuss a new topic here, which are active filters. And we sort of mentioned that very early on, we were talking about filtering way back in the first weeks when we started to talk about power supplies. You remember you have the rectifier circuit, and coming out of the rectifier circuit was a half wave or a full wave rectified sinusoidal signal. And to smoothen it out, we took that half wave signal and we passed it through a simple capacitor, a large capacitor as it turned out, and that plus the load of the what do you call it, the circuit following formed a simple RC network that worked as a filter and basically took out the fluctuating DC, the fluctuation part, and you were left with a fairly reasonable voltage that you could now use something for. Well, that was in fact a filter, a passive filter. So today we're going to do, we're starting to talk a little more formally about filters and what filters mean. Filters now are circuits that are designed to pass a specific band of frequencies while attenuating all the signals outside of this band. So as you can imagine, in the whole electronics world and in engineering, especially electrical engineering, signals pass back and forth. We've spoken about that, things that are being controlled, where there's motors, machines, valves, or you're talking to someone, you have a signal going down the road, and usually the signal gets affected by the circuitry, it gets affected by other components. And when it reaches its destination, the signal is there, but it has a lot of other baggage that it accumulated along the way. And that baggage, collectively, we call in engineering noise, right, which is unwanted stuff. We use filters to now get rid of the noise and hopefully get back the original signal that we wanted. Passive filters, now there are two sort of flavors of this. The passive filters only contain resistors, inductors, and capacitors. So your basic RLC network in whatever sort of combination, series, parallel, and both, will, as you analyze them, they will have a response to some frequencies. It would pass some others, and others it would not allow to pass. The thing with passive filters is that the signal that it eventually allows to pass is usually quite significantly attenuated, especially if the filter is a large filter. And we'll talk about that, what you call a large filter, in a little while. So that if there's an alternative to doing that, it is preferred. And this is where active filters come in. So active filters take the same passive components, resistors, inductors, and capacitors, mostly resistors and capacitors, and they add some electronic active components alongside them, which would be like transistors, or in most cases, an operational amp. And what happens is now that because you can set the gain of the amplifier, you can amplify the signal to compensate for any losses that were incurred because of the filtering process. So you're able to get back the signal to some level close to what it was intended to be. All right, and there are more, so in terms of categorizing filters, there are really four general bands or categories of filters. There are the low-pass filters, the high-pass filters, the band-pass, and the band-stop. And we'll see the characteristics in a second. Right, the other term you sometimes see for the band-stop filter is something called a notch filter, and you'll see why in a second. Right, and filters, usually we describe filters in terms of the type of filter. So here's a diagram, and you will see on the x-axis an approximate span of frequencies going from, well, 1 hertz, very low, almost DC, all the way up to a gigahertz here. Right, and you can which is about the upper limit. You can get some slightly higher frequencies as you go along. So the filter type in terms of the mechanism for filtering. So like LC or RLC filters will, which is the top black bar, you can see that you can get from fairly low frequencies, which is about 100 hertz, all the way up to almost a gigahertz using the passive components. And they are used a lot. They are used a lot in radio frequency circuits and communication circuits and the like. So they I mean, simple radio communication, two-way radio or radio that you might have in your car and so on. There are LC filters inside of there that help to tune the particular radio to a channel or to a frequency. The active filters, which is the second bar, runs somewhat lower in its upper frequency simply because it's limited by the frequency response of the operational amplifier. Now, there are modern op amps that go up very high in frequency, so it's possible to get active filters now that are going up almost to the gigahertz range as well. Of course, designing those is a whole study of its own on how it's not things that you can breadboard and make, as we mentioned before. These are things that have to have printed circuit boards and specially designed printed circuit boards at that too, where even the copper traces on the circuit board form part of the inductive or capacitive behavior of the filter. And then the third bar is the crystal filters. We did a little chat on crystal oscillators last time, and we saw that the piezoelectric filters, or the piezoelectric behavior of a quartz crystal allows it to be very selective in terms of passing frequencies. So you can use that to great effect to filter particular frequencies that you might want and not to pass others at all. And then there are mechanical filters, and you know a simple one already, which would have been the shock absorber system for a car, which is a dashboard spring system, which basically absorbs the vibration of the road. Now they use these a lot, for instance, in when you're mounting heavy equipment, machinery, motors, and generators and the like. They mount them on special stands that may have like use very thick rubber compounds or combination of spring and rubber compounds, so that when the device is rotating at high speed, the floor that it is mounted on doesn't vibrate. Okay, and you would find that in big industrial plants, or you would find that you go down right in power gen and by the large generators, how they're mounted. The filtering to absorb the vibration of the generator is mechanical. Yeah, and you've met again. You met that by driving to wherever you happen to go today. You were on a mechanical filter of some sort. Yeah, and of course, how we characterize the filter in terms of how good it works are by a couple of terms that you will see. We wouldn't cover all of them, but you will meet them as you go through. The filter has what is known as a pass band. Right now, the pass band, of course, are the frequencies that you want to let through. And then next to it, after it reaches a particular frequency that we call the cutoff, it is supposed to stop letting anything through. So ideally, an ideal filter is supposed to pass everything in the pass band, and then as it reaches the cutoff, it stops. And then everything in the next band, which is what we call the stop band, is supposed to be stopped, absolutely stopped. So the red line is how an ideal filter is supposed to work. Well, we know nothing operates like that in the real world. So typically filters they don't go suddenly from the pass band to the stop band. There's a segment between the two where it goes from one to the other, and we call that the transition band. The better the filter, the sharper the transition band is. So a very, very good filter will have a very sharp transition band, and then it goes into the stop band. And then how it behaves in each band is also an issue. Some filters have what is known as a pass band ripple. So inside in the pass band itself, It's passing the signal, but it has some little ripple. And then it stops. And in the stop band, it just doesn't simply switch off, but it also has a little ripple inside of there. So it's bouncing up and down in the pass band and also in the stop band as well. The better filters will have, typically have something relatively smooth in the pass band, a fairly smooth transition to the stop band, something looking like that, all right? With minimal ripple in the stop band and minimal ripple in the pass band, okay? But they are all types, and it depends on the particular application that you are after. When you do, if any of you all do ECNG2012, you will go through some of this thing with a selection of circuits that have this sort of behavior, and you're able to select the pass band, the sort of pass band ripple, and the stop band and the stop band ripple and the like. So the ideal model, and I'll have to do over this diagram at some point in time, the ideal model doesn't pass anything until some band. It lets everything pass without doing anything to it. So here, there's no distortion here. In other words, the amplitude doesn't change of the signal, or the phase of the signal doesn't change at all. And then you reach some, so this will be like the F cutoff lower and the F cutoff higher, right? Frequency, just for argument's sake, this one is a band pass, and we'll see that in a second. And it reaches the upper frequency, and then it just knocks off here. Now, there are all sorts of ways to create, or what they call to realize the filter. And everybody tries to get as close to this sort of behavior as possible. And there are versions of that are around, and they're named after the people who created the version. So you're going to see names like Butterworth somewhere in your program, Chebyshev, Bessel, and there are a whole other numbers. We're not going to spend too much time on these, but in general terms, most of what we're going to meet in this course is Butterworth, right? Butterworth, right? The Butterworth filters are the ones that we are going to meet predominantly in our conversations. And filters are defined by a transfer function. And we know this already. The transfer function is a ratio of two polynomials in the S domain. Okay, the roots of the polynomials, you know already, the poles and the zeros. If the zeros are the roots of the numerator, the poles are the roots of the denominator. Those are significant in the behavior of that transfer function. We got a hint of that already, right? And we're discussing the Fourier transforms in signals and systems. So you can know already, if you have a transfer function and you make the substitution x equals j omega, you can now see how it behaves in frequency, which is what we're going to do. And also later on, in ECNG, in Signals and Systems 2011, we're going to cover something called Bode or Bode plots, named after somebody named Henry Bode, a Dutch communications engineer who came up with this particular plot. You're going to see it in this class, what it looks like, but how we go about doing it will be covered in the other course. All right? So a low-pass filter, the first one, the low-pass filter, has it produces a constant voltage output from DC up to some cutoff frequency, and then above the cutoff frequency, the response is attenuated. So the ideal low-pass filter, right, is going to do this sort of behavior. This is the kind of filter that you use, for instance, with a power supply, because the power supply, you want to pass DC, right, from the half wave or full wave rectified signal. What you want is to get rid of that ripple and let the DC component, remember there's a DC average here. You want this to pass and you want to block the ripple, right? So low pass filters would be used a lot in things like power supplies, and in a number of other low frequency operations, right? The cutoff frequency as a general thing, the cutoff frequency is also called the 3 decibel frequency, and you'll see that in a second why. The corner frequency, because there's a corner, or the break frequency where it goes from, it breaks. So the line goes on, it just breaks, yeah? The high pass filter goes the other way. The high pass filter blocks everything from DC up to some frequency. And then at the cutoff frequency for the high pass filter, it starts to let everything pass, ideally. Okay? So these sort of filters now you see in certain types of communication work. You also see it in audio circuits, for instance. So like the low pass filters from the, if you go back here, the low pass filter in an audio system, those of you into loudspeakers and so on, the low pass filter would be the one that would send the low frequencies or the bass frequencies. Right, so these are the ones that go to the large speakers, the big low frequency speakers that you have around. And then the other side now, this would pass the high frequencies, right, which would be what you sometimes call the treble frequencies, the middles or the mids or the trebles. And these go to the smaller frequencies, or like we mentioned last time, the piezoelectric speakers and so on. Right, so an application of that is straight in the audio field if you enter that. The band pass filters pass a particular range of frequencies within a band. So there's a lower cutoff and there's a higher cutoff. It passes everything between that and it rejects everything outside of that. These you meet a lot in communication circuits, for instance. So you're tuning into a particular channel, a radio channel. So you're tuning into something. I don't know. What's your favorite? Those of you who still listen to anything on the radio, what sort of frequency you listen to? What's your favorite channel? Okay, so 95.1. So Java listen to 95.1. So the carrier frequency is 95.1 megahertz. Right? The law is for, this is FM, and you'll meet this in your comms if you haven't as yet, 95.1 megahertz. So the carrier frequency is 95.1 megahertz. And by law, you have a limit. You have plus or minus 200 kilohertz. Right? It's a 200. I think it is. Is that a plus or, yeah, it should be 200 kilohertz, right? By law. So in other words, if you have another station close to 95.1, you have to be at least 200 kilohertz away so they don't interfere with this. So in order to tune 95.1, your radio, the center frequency here is going to be the 95.1. And the tuning circuit in the radio is going to have a bandpass filter that is going to lock in to a range of frequencies plus or minus 200K around the 95. And everything that is in there, it will associate with the 95.1 frequency and then extract the audio and play it. Anything outside of that, which would be like from an adjacent signal, there are 94 point something signals and there's 96 point something megahertz and so on. It will reject those. Yeah. So this is all over the place in communication. And Dr. Radix mentioned it in her talk with Analog Meets Digital when she spoke about something called aliasing. So look over that and you'll see she mentioned filters inside of here and aliasing and the use of filters in stopping that. All right, so you'll go back and when you check our notes and listen to that lecture again, you will come across that. And then the last category are the notch filters. So the notch filters basically let everything pass apart from a range that it stops in the middle. A notch, or it's a band stop or a notch. So you notice like this is going here, and we have a notch that knocking out something in the middle. And you see these a lot, for instance, if you've ever been in a public address system and you're hearing feedback, the high-pitched whistles. that happens when, for instance, a microphone is too close to a speaker. The modern mixer systems and amplifier systems for those sort of performances have what are known as active notch filters. So once the feedback starts, which is usually, so you have a frequency, and then at some point in time at a frequency, a very high pitch will start to develop because of somebody's microphone is too close to a speaker. Then what the system does, so you have the amplitude of the sound going to the speaker, and it suddenly starts to peak very high at a particular frequency, which is the whistle that you hear. What the system does, or the person on a mixing board, for instance, will do manually, is to put a notch filter right here. So you put a notch filter on that does this. So it's passing everything and it's notching out this particular, in other words, rejecting this frequency. So as soon as it detects the high pitch, the system or the user will put, the system or the user will put a notch right there, and it knocks off that particular feedback for you, and everything stabilizes again. All right. Okay, so next slide. Right, so let's look a little bit more into this and start. Our first look now will be on the first order low pass filter. So the first order low pass active filter has one pole in the transfer function. We're not using any capacitors, so the pole in the transfer function is created by the capacitor. Right? The circuit, in this case, the circuit has a non-inverting low pass amplifier, right? And it's basically a unity gain. So this one doesn't have any gain as yet. So let's see how that works and some other things that we'll discover as we go through that. Right? So the transfer function, if you look at the transfer function for this, the input and output, remember the output, because there's a unity gain buffer, here is VO as well. So if you work at V out over V in, very simple, it's an impedance divider, essentially. So the transfer function is 1 over 1 plus SCR. And we just, we learned from before that if you want to see what a frequency transfer function looks like, we make the substitution S equal to J omega. And we have that the frequency response transfer function is 1 over 1 plus J omega CR. Now, by definition, this is a definition here, a definition. They define the cutoff frequency for a filter as the value of frequency where the amplitude, the magnitude of the amplitude in the passband drops to 0.707 or 1 over root 2. Well, 0.707 is 0.7071. Actually, it's 1 over root 2 of the passband value. So you have a passband and the response starts to drop. The cutoff frequency, because it's not ideal, remember, it doesn't suddenly change. This cutoff frequency here is where this value is 1 over root 2 of the passband value, or about 70% if you like, 70.7% of the passband, right? It is known as a half power point, which is where the 1 over root 2 comes in. If you were dealing with power, it would have been where the power in the particular signal, where the power drops to half, right? And since power is amplitude squared is proportional to amplitude squared, then the amplitude will be 1 over the square root of that, which is 1 over root 2, right? You would have learned that from your circuits early on. So if you plot the frequency response, the magnitude of the frequency response for the simple first order low pass filter, this is what the response looks like. Now notice that it starts, and we can see some things already from it. So it's passing and then it is changing from an amplitude, from a magnitude, and the magnitude is fairly low here because of the values that I used to draw it. But so forget the actual values there on the y-axis, but it's dropping from some value and then going down to a much lower value. So this is the typical response of a low-pass filter. What happens though is that there's another drawing that we use that gives a little more complete picture, and it allows us to compare the performances of different types of filters on an easier basis. But just off of this, if you were to watch the diagram here, let me zoom it up a little bit, right? 0.7 is somewhere around here, right? So we're going about here. So 0.7 would be about here. So in other words, this particular filter has a cutoff frequency of 100 radians per second, right? 100 radians per second. And of course, you could convert this very easy to hertz, right? This will be the cutoff frequency in hertz. Oops. The cutoff frequency in hertz is, of course, would be 1 over 2 pi RC, right? So it's easy to go from one to the other. So you can see that the 0.707 point is about 100 hertz for this. In other words, the cutoff frequency is 100, sorry, not hertz, 100 radians per second. But notice here, ideally, therefore, if this was a perfect filter, it should have been doing this, right? Notice how far this is. Of course, this is a first order filter, but notice we are quite away from the ideal performance at this point in time. Yeah? Feel free to stop anytime or make any comments related to this, okay? Ask any questions. So what we normally do, though, is instead of using a magnitude plot like we have here, what we normally do is to use a logarithmic plot. The log plot, we plot the magnitude of the response in decibels, and we also use a log scale for the frequency. Now, first off, in decibels, again, you would have met this before. To convert a number from a value into decibels, it is 20 log to the base 10, of course, of the number, right? Usually decibels are a ratio, but just as a plain, if you want to express a number as a decibel is really supposed to be a ratio to some standard. But here, if you express it as you could consider it a ratio of something to 1 for argument's sake, is 20 log to the base 10, log base 10, remember that. So if you were to draw the same response on this slide here, let's get rid of the trash a little bit. If I were to draw this response now using a log scale, this is what the response looks like. And you're able to see, I mean, zoom it up a little bit. All right, we can see some things already. So in the pass band, okay, so it's going here, and then it starts, the frequency response starts to fall off. All right, and then just a couple of things now. We use a log scale for the frequency. That allows us to compress the diagram into a much smaller space. Notice here, this is 1, this is 1, this is 10, 100, 1,000, and 10K radians per second. Each of these, each space is 10 times the frequency interval of the one before. So this one is going from 1 to 10. This one is 10 to 100. This one is 100 to 1,000. They call that frequency range a decade. Right? So by plotting it now, I can express, notice I have a very large frequency range here, which is up to 10 kilohertz, 10 kiloradians per second on a fairly small scale in a diagram. And in fact, I can add 2 extra points and go up to 1 million radians per second without having an exceedingly large diagram. So it's very compact. Yeah. So keep this in mind, and then look at this. Look at this line here now. Look at this blue line here, and tell me this space here is a decade, right? What is the slope of this line over that period of time? It is starting here and ending here. So at this point, the value is what? The value of the response at that point is what? If you read the axis, minus 60. And the value at this point is minus 80. Right. So over the decade, the response fell by minus 20 decibels. Okay? In other words, this slope here, we say that that slope is minus 20 decibels per decade. Right? That is characteristic of a first order transfer function, and we're going to meet that in signals too. So all first order transfer functions of this behavior, this one has, notice, and we kind of doing two things in one. This is a transfer function here. It has no zeros, and it has one pole, right? So a transfer function that has no zeros and one pole, like this, first off, behaves like a low-pass filter. And second, when you draw the frequency response decreases at the rate of minus 20 decibels per decade. Yeah? Make sense? You probably covered this elsewhere. I'm not too sure, but if so, it's a nice revision. But everybody following? Yeah, no, maybe. All right? So all first order transfer functions, single pole first order transfer functions actually will decrease at 20 decibels per decade. And we're going to see how to plot that without even plotting frequencies when we do Bode plots in signals. Right. So as I said before, one of the things about using the operational amplifier, yes, you could use it as a unity gain buffer like we did before, but usually we want to compensate for the signal loss. So you can put gain on the op amp, and that is just simply because of the configuration. If I put a feedback on a ground resistor on the op amp, then I have a non-inverting amplifier with gain, and the gain of the amplifier is, of course, the 1 plus RF over RA, plus the frequency response of the RC network. This is the part that is the frequency selective part, and the op amp is providing the gain. All right, and remember, electronically speaking, for the op amp, these 2 points are, as far as the circuit is concerned, those 2 points are the same, right? They're connected, the virtual earth behavior. So the cutoff frequency is still the same, 1 over 2 pi fc or 1 over RC radians per second. Now, to get a high-pass filter, what we do is to interchange the resistance and the capacitors. If you go back here briefly, you remember how, again, intuitively, we had covered this before. In a circuit like this one, at low frequencies, the capacitor is essentially an open circuit. So the circuit, whatever voltage is coming in here will go through to the op amp and go out. As the frequency starts to go up, the capacitor impedance starts to drop. So it progressively shorts more and more of the signal down towards ground. So what happens is that as frequency goes up, as the capacitor starts to short it, now the amplitude of the signal will drop. That is a low pass behavior. If you interchange the positions of the capacitor and the resistor, the reverse is going to happen. So at this point in time now, at low frequencies, this is an open circuit. If there is an open circuit, it means at low frequencies, nothing is going to get through from V in. As the frequency starts to crank up though, the capacitor starts to conduct more and more. So as the frequency goes up, now at low frequencies, you're not letting anything through, but as the frequency starts to go up, the capacitor lets signal through. So you're getting the opposite behavior. This is the high pass filter behavior now. And if you do the circuit analysis that we did before, the transfer function now for the high pass filter has a 0 and 1 pole. So it has added one more component to the transfer function that we had before. You plug S equal to j omega into it, and we now have the frequency response transfer function, and the same definition applies now. We looked at that. The cutoff is where the magnitude of that response is equal to 1 over root 2, like we did before. If you do that, you're going to get exactly the same cutoff frequency, which is omega c is 1 over RC, as for the low pass case. But look at the response in the log. When you plot the log scale now, look at the response now. It starts low, so there's nothing, not passing anything, and then we get it. Forget the phase for the instance. We will talk about that in signals and then come back to hear why the phase does that. Right, but it's the upper diagram, the magnitude versus frequency response. And again, if you check the slope here, right, you're going to get what this time? What does that slope look like? This space is a decade. Exactly. So the slope here, you notice over the decade, it's going from 0 to 20. So in other words, the high pass filter response is plus 20 dB per decade, right? The low pass is minus 20 dB per decade. The high pass is plus 20 dB per decade. That is the effect of the 0 in the response. And we will see how that turns out, as I say, when we talk about both plots later on. And then, of course, what I could do is to add gain to that. So the same thing, notice I have the resistor and the capacitor interchange, but I can now add an inverting amplifier with gain to it. So here is a high pass filter with gain. Yeah? Fair enough? So questions? Take some questions here, and then I'll stop today because the next time we're going on to the higher order filters. Exactly. So that's a very good question, Jawad, and in fact, that is how one way of doing it. So just think about it. If I have, this is my frequency response here. So if I take a low pass filter, so a low pass filter does this, right? And a high pass filter that does this. If I cascade them, and notice they sort of sequence. If I cascade a low pass filter and a high pass filter, I'm going to get a response that looks like this, right? Which is my band pass, right? And in fact, that is one way of creating a band pass filter results, right? That's one way of doing it. And tomorrow we're going to take, it is two steps, well, yeah, two-step responses. Tomorrow we're going to discuss that in some detail, and we will look at higher order filters. So because our first order filters you saw, it rolls off, but it rolls off very slowly. And eventually, and for most applications, that isn't enough. So if you need the higher order filters, then you need to go and add additional components. So in tomorrow's class, and remember I'm running the class tomorrow just from 10 to 11 to give you all time because of the exam in the afternoon. Tomorrow morning, we're going to discuss higher order, well, second order low and high pass filters, and start looking at band pass filters as well, which will further answer Jared's question. Yeah? So any other questions? Comments? Yeah? All right. So that's it for today. Relatively short. Well, not too short. We're just 5 minutes behind where we were. Right, but just to introduce this, and tomorrow we will spend some time and look at the higher order filters and then see how we cascade and make higher order filters going forward there and the types that are available. All right, so I will stop there.